to each and every one of you, and welcome back to another lecture video discussion. So for today we will be discussing all about radiation and matter. So the outline of our discussion for today will be all about interaction mechanisms, which will be all about absorption, scattering, and penetration. And then will be the radiation types and matter interaction, which will be all about the alpha, the beta particles, as well as the gamma rays and the X-rays. And then we will also be discussing all about linear energy transfer and also the radiation dissymmetry. Okay, so let's jump in. So now here, radiation interacts with matter through several mechanisms. So again, it includes the absorption, the scattering, and also penetration. So as for the absorption, if we will define absorption, it refers to the process where radiation transfers energy to the atoms or molecules of the material it passes through, so leading to various physical changes. So there are different types of radiation that undergo distinct absorption mechanisms depending on their nature. So the first one is what we call the photoelectric effect. So this is the first one, photoelectric effect. This is for the electromagnetic radiation. So now, as for the photoelectric effect, this is what happens during the photoelectric effect. So here, when X-rays or gamma rays pass through matter, they can transfer their energy to an inner shell electron of an atom, which causes the electron to be ejected. So, the energy of the incident photon must be greater than or equal to the binding energy of the electron. So, this process or the photoelectric effect is more likely at lower photon energies for atoms with high atomic numbers. So that is the first one. Okay, now the second one is what we call the ionization. This is for charged particles. So here, as for ionization, gi-explain din na when alpha or beta particles pass through matter, they interact directly with the electrons of atoms, ionizing them by transferring energy and knocking electrons out of the atom. So now the radiation loses energy as it ionizes the material, eventually stopping. And then we have the third one, which we call as the excitation. So in this case, radiation transfers energy to an atom or molecule, raising the electrons to higher energy levels without ejecting them. So the excited atom later releases energy by emitting photons that is often as visible as light or heat. So those are the different types of radiation that undergo distinct absorption mechanisms. So we have again the photoelectric effect for electromagnetic radiation. We also have ionization for the charged particles, and then we have the excitation. So that is for absorption. Now we go to scattering. So scattering occurs when radiation changes direction after interacting with matter. So either losing energy in the process or retaining it. So there are two very important scattering mechanisms, so which we call as the Rayleigh and also the Compton scattering. So see, Rayleigh scattering is also known as the coherent scattering, which we'll be discussing later on. What do we mean by this one? And then we have the second one is the Compton scattering, or also known as the incoherent scattering. Now let's dive into Rayleigh scattering, or again also known as the coherent scattering. So now Rayleigh scattering, in this process, an incident photon interacts with an atom or molecule, causing the atom's electrons to vibrate and also re-radiate the photon in a different direction. So the photon does not lose energy in this process. So we call Rayleigh scattering as elastic or elastic scattering. So this type of scattering is more significant at lower photon energies, that is, for example, visible light, and does not cause ionization. So that is for the Rayleigh scattering or Rayleigh scattering. Now for the Compton scattering or the incoherent scattering, so this occurs when a high energy ng photon, for example, an X-ray or gamma ray bakaha, collides with a loosely bound outer electron in an atom. So the photon transfers some of its energy to the electron, now causing the electron to be ejected from the atom. Now, the photon is scattered in a new direction with reduced energy na dayon. So, kani siya nga process is important for higher energy photons and leads to both ionization and energy loss in the photon. So, that is the Rayleigh or Rayleigh scattering and also Compton scattering. So again, these two are very important scattering mechanisms. And then the third one is what we call the penetration. So the penetration depth of radiation depends on its type, depends on the energy, and also depends on the material through which it passes. So as for penetration, we will be discussing the penetration on alpha particles, beta, gamma, and also the neutrons. So let's start with our alpha particles. So the alpha particles, these are heavy, positively charged particles that interact strongly with matter. So now, due to their large mass and charge, they quickly lose energy through ionization and also are easily stopped by a few centimeters of air or a thin sheet of paper. So they have very low penetration power. So very low ang penetration power ni alpha particles. Now as for the beta particles, these are lighter. So kung si alpha is heavy, si beta is lighter, high energy electrons or positrons that have greater penetration ability than the alpha particles, but can still be stopped by a few millimeters of aluminum or plastic. So they lose energy, makukuhaan sila energy through ionization and Bremsstrahl lang. So kani si Bremsstrahl lang is the radiation due to the deceleration. So that is for the penetration for beta particles. Now, how about for the gamma rays and X-rays? So kani sila, si gamma rays and X-rays are high energy photons that interact with matter primarily through the photoelectric effect, Compton scattering, and also pair production, so at very high energies. So they are highly penetrating and require dense materials like lead or thick layers of concrete for shielding. So inana ang penetration ni kailangan og dense materials para makapenetrate si a highly penetrating si gamma rays and X-rays. So we need dense materials like lead or thick layers of concrete for shielding this gamma rays and X-rays. And then we have the fourth one, which are the neutrons. So si neutrons, being again neutral particles, do not directly ionize atoms, but they interact with the atomic nuclei. So They are highly penetrating and best shielded by materials rich in hydrogen, like for example water or concrete, which slow down the neutrons through elastic scattering. So again, si elastic scattering is si Rayleigh scattering. Okay, or an example of an elastic scattering is si Rayleigh scattering. So those are, to sum up this discussion or this topic. So we will define absorption, scattering, and also penetration. So si absorption, it transfers energy to atoms or molecules resulting in ionization or excitation. And then for the scattering, as of scattering, it changes the direction of radiation and in some cases reduces its energy, like in Compton scattering. And then for the third one, we have the penetration. It varies with radiation type. So with alpha particles being the least penetrating and gamma rays or neutrons being the most penetrating. So that is for our first topic on according to the outline of the topics that we will be discussing today. Now, let's proceed to the next topic. So our next topic will be all about radiation absorption mechanism. So the process of radiation absorption by matter, it involves the transfer, or there is a transfer of energy from ionizing radiation, let's say the X-rays, the gamma rays, alpha, beta particles, and neutrons, to the atoms and molecules within the material. So, kani siya nga energy transfer can lead to several effects on the material's physical and chemical properties with important implications for radiation protection. Now, as for the radiation absorption mechanism, so now, when radiation interacts with matter, it can be absorbed in different ways. So, depending on the type of radiation and also the nature of the material. So, let's start with photoelectric effect. So, again, di ba na-discuss na nato si photoelectric effect, but let's dig deeper onto photoelectric effect. So, photoelectric effect, this is what happens during the photoelectric effect. So, this occurs when a photon, typically an X-ray, baka or gamma ray, interacts with an atom and transfers all its energy to an inner shell electron, causing the electron to be ejected. So this process is what we call the ionization. Now the atom is left ionized, and also the secondary processes such as characteristic X-ray emission or Auger electron emission can occur during this process. So the probability of the photoelectric effect increases with the atomic number of the material and decreases as the photon energy increases. So that is what is happening during the photoelectric effect. Now, let's proceed with Compton scattering. So again, on this figure, this is an example of what happens during the Compton scattering. So in this interaction, the incoming photon transfers part of its energy to an outer shell electron, ejecting it from the atom. So now the photon is scattered in a different direction with a reduced energy na. So this is a key mechanism for medium energy photons such as gamma rays and X-rays, and results in both ionization and energy dissipation in the material. So that is Compton scattering. Now, how about this third one? This third one is what we call the pair production. So, si pair production, again, in this figure, this is an example of what happens during a pair production. So, as for pair production, when a high energy photon, which is above 1.02 mega electron volts, passes near the nucleus of an atom, so it may be absorbed and converted into an electron and a positron. So here, according to the figure, this is what happens during pair production. So this process happens at very high photon energies and is significant in materials with high atomic number. So now the electron and the positron eventually lose energy through ionization and annihilation processes. So that is what is happening during the pair production. The next one is ionization by charged particles. So what happens during the ionization by charged particles? So now the alpha and beta particles, which we call as the charged particles, directly ionize atoms as they pass through a material. So the alpha particles, diba, si alpha particles are more massive and heavily charged. So they ionize more densely but have a shorter range, while si beta particles ionize more diffusely but they penetrate deeper into the material. So that is how we would explain ionization by discharged particles or by alpha and beta particles. And then we have the last one, which is all about neutron interactions. So here in this figure is what is happening during of the neutron and the nucleus before the collision. So see, neutrons, they can be absorbed, they interact with the nuclei rather than the electrons, by the way. So see, neutrons can be absorbed by the nuclei, causing nuclear reactions such as neutron capture or neutron fission. So since the neutrons are uncharged, so they can penetrate deeply into the materials before they interact. So now the neutron absorption often produces secondary radiation such as the gamma rays or charged particles, so which can further affect the material. So those are the radiation absorption mechanism. So meaning it can be absorbed in various ways or in different ways depending on the type of the radiation and also the nature of the material. Okay, so now question here is, what are the effects of radiation absorption on material properties? So the absorption of radiation can induce significant changes, so in the physical, the chemical, and also structural properties of the materials. So these changes are primarily driven by the ionization and excitation of atoms and molecules. So now, what are the effects of radiation? Now the first one is ionization and chemical changes. So the ionization of atoms and molecules can disrupt chemical bonds, creating now the free radicals or what we call the ions. So now also in biological materials, this can lead to cellular damage, DNA mutations, and also potentially cancer. So in non-biological materials, si ionization daw can cause oxidation, chemical degradation, or cross-linking of polymers. So those are the effects of radiation absorption on these material properties. Now the second one is structural damage. So now high doses of radiation or exposure of high doses of radiation can cause displacement of atoms within the material, leading to lattice defects in crystalline solids. So this is particularly significant in materials such as metals and semiconductors, wherein the radiation-induced defects can alter electrical conductivity. We have the mechanical strength and also the thermal properties. So that is the second effect of radiation absorption. The third one is the thermal effects. So as radiation energy is absorbed, part of the energy is converted into heat. So this can cause localized heating, potentially altering the material's temperature, the phase, or even causing melting in extreme cases. So the heat is generated, or the heat generated can also exacerbate other forms of damage. And then we have the fourth one is the color changes. So radiation can cause defects in the crystal structure of transparent materials such as glass or gemstones, resulting in color changes. So for example, radiation can induce radiation-induced coloration in some crystals and also optical materials. So exposure of radiation can cause or can cause defects on this crystal structure, such as again the glass and also the gemstones. So those are the effects. So we have 4 effects of radiation absorption on the material properties. Now, what are the implications for radiation protection? So as for radiation protection, so understanding the process of radiation absorption is very crucial for designing the effective radiation protection strategies. So the ang goal gid nato sa radiation protection is to minimize the exposure of humans and also sensitive equipment to harmful ionizing radiation. So if you have noticed, in the hospitals, natay x-ray nga room. So as you can see, the rad techs or the radiology technicians, they wear some equipments or some what do we call that, shielding materials, para they will not be so overly exposed to radiation. Okay, since mo magin na ilang job, so they need to be there. So para to minimize the exposure, their body to the exposure of radiation, so they wear protective nga mga shielding. Okay, so what are the implications for radiation protection? The first one is shielding. So from the word shield, so different types of radiation require different types of shielding materials. So okay, di ba? Si alpha, si beta, si gamma rays, and neutrons have different radiation nga penetration. So we need different types of shielding materials depending on the different types of radiation. So as for the alpha particles, so they are easily absorbed by a sheet of paper or a few centimeters of air. So, you mentioned diri, minimal shielding is needed. Now, as for the beta particles, they require materials like plastic, glass, or aluminum to shield them. And as for gamma rays and X-rays, they are highly penetrating and require dense materials like lead or thick concrete for effective shielding. And as for the neutrons, they require materials rich in hydrogen, such as water, we have the paraffin, or even concrete to slow them down through elastic scattering before they are absorbed. So, again, the first implication is the shielding for radiation protection. Now, the second one is dosimetry. So, si dosimetry, if we will define dosimetry, it is the amount of absorbed radiation, which is measured in terms of the absorbed dose. So we will be discussing later on, or later part of this discussion, what is an absorbed dose. So which is expressed in the units of Grace. So shortcut of the unit of Grace is GY. So 1 gray corresponds to the absorption of 1 joule of radiation energy per kilogram of matter. So also, the biological effects of radiation are expressed in sieverts or SV, which take into account the type of radiation and its biological impact. So later on, again, we will be discussing kinsa ni silang Grace, kinsa ni si sieverts. So again, those are the units of radiation. Okay. And then we have radiation protection involves monitoring these doses to ensure they remain within safe limits. So I think some of you have watched movies regarding with like radiation or even katong nuclear nga itong sa Japan. So, as you can see, there is a safe limit or safe number of dose. And then, pag mulagpas na kaana that is very harmful to the human body. Okay. We also have the biological damage. So, this is the third implication. So, the absorbed radiation can cause direct damage to the living tissues through ionization and molecular disruption, particularly in the DNA. So, this can result, again, in cellular mutations, carcinogenesis, or even cell death. So, for radiation protection in medical or occupational settings, so limits are placed on exposure to minimize the risk of radiation-induced diseases. And then we have the fourth one, or the fourth implications for radiation protection is we have the time, the distance, and shielding. So these are the three fundamental principles of radiation protection. Now, as for the time, so when we say time, reducing the time spent near a radiation source reduces exposure. As for the distance, increasing the distance from a radiation source reduces exposure due to the inverse square law. And then, as for the shielding, we have using appropriate materials to absorb or block radiation reduces exposure. So that is how we would reduce the exposure of radiation. So again, time, distance, and shielding. Okay, so radiation absorption by matter involves energy transfer mechanisms like ionization and excitation, which can lead to chemical, structural, and thermal changes in the material. So kani sila nga mga changes have a critical implications for radiation protection, including the design of the shielding, also understanding the biological effects of radiation, and limiting the exposure through the principles of, again, we have the time, distance, and shielding. Okay, so now let's dig deeper onto the scattering. There's two types of scattering atong na-discuss na for a little bit, which again are the Rayleigh scattering and Compton scattering. So these two scatterings, or these two, are different types of photon scattering processes that occur when radiation interacts with matter. So they both involve the deflection of photons, but they differ in the way energy is transferred and also the impact that they have on radiation behavior. So let's talk about the difference between the Rayleigh scattering and Compton scattering. Now let's start with the Rayleigh scattering, or again, coherent scattering. So this is the figure of what happens during the Rayleigh scattering. So as for the nature of interaction, Rayleigh scattering, also known as, again, coherent scattering, occurs when an incident photon interacts with an entire atom or molecule, causing the electrons in the atom to oscillate collectively. So the oscillating electrons then re-emit the photon at the same energy or frequency, but in a different direction. So that is the nature of interaction of this scattering. Now, as for the energy transfer in Rayleigh scattering, there is no energy transfer to the atom or the molecule. So katong scattered photon retains the same energy as the incident photon, meaning that the Rayleigh scattering is an elastic scattering process. Now, what are the conditions of Rayleigh scattering? So the Rayleigh scattering is the most significant So most significant daw si Rayleigh scattering at low photon energy such as visible light or low energy X-rays, and in materials with small atomic numbers. So it is inversely proportional to the fourth power of the wavelength of the radiation, meaning that the shorter wavelengths, for example the blue light, they scatter more than longer wavelengths, which is, for example, the red light. So kani siya nga phenomenon explains the blue color of the sky. So that is the condition for the Rayleigh scattering. And what is the impact of Rayleigh scattering on radiation behavior? Now, since Rayleigh scattering is elastic, it does not reduce the energy of the photon, but changes its direction. So, dili niya gina-reduce ang energy sa photon, but ilang i-change ang direction. So, kani siya nga process has a little impact on the overall energy deposition in materials, as no ionization occurs. And then, so si Rayleigh scattering also is less significant in high energy photon interaction, such as with gamma rays, where other scattering processes dominate. And also in X-ray imaging, si Rayleigh scattering contributes to the image noise without degrading the energy of the radiation. So that is the impact of Rayleigh scattering on the radiation behavior. Okay, so we are done with Rayleigh scattering. Now let's proceed to Compton scattering or incoherent scattering. So again, as for the nature of interaction ni Compton, so it is also known as incoherent scattering. So Compton scattering occurs when a high energy photon, typically whether an X-ray or gamma ray, collides with a loosely bound outer electron of an atom. So the photon transfers the part of its energy to the electron, ejecting it from the atom. So this process again is what we call the ionization. So ang photon na karon continues with reduced energy na in a different direction. So that is the nature of interaction of Compton scattering, or what is happening during the Compton scattering. Now, how about the energy transfer for Compton scattering? As for Compton scattering, the incident photon loses part of its energy to the electron, making this an inelastic scattering process. So, kung si Rayleigh is an elastic scattering process, si Compton is an inelastic scattering process. So the scattered photon has a lower energy and a longer wavelength compared to the original photon. So now, ang amount na din sa energy that is transferred depends on the scattering angle. So which means that larger scattering angles result in greater energy loss. Again, larger scattering angles results in greater energy loss. Okay, so how about the conditions of Compton scattering? So si Compton scattering occurs with high energy photons such as X-rays and gamma rays, and also it is more likely in materials with loosely bound outer shell electrons. So it becomes the dominant interaction mechanism for photons in the intermediate energy range, which is between 100 kilo electron volt and also a few mega electron volt. So that is a condition of how Compton scattering would occur. Okay, now what is the impact of Compton scattering on radiation behavior? So si Compton scattering plays daw a major role in radiation transport, especially for gamma rays and X-rays that are used in medical imaging, industrial radiography, and also radiation therapy. So what happens is it reduces the energy of the scattered photon, contributing to dose deposition within the material and leading to ionization, which can damage biological nga tissues. So Si Compton scattering is responsible for degrading image contrast in X-ray and gamma ray imaging due to the scattered radiation reaching detectors from various directions. And in radiation protection, the scattering of high energy photons increases the need for, again, shielding, as the scattered photons can travel in different directions and deposit energy over a larger area. So, kailangan gid siya og bigger shielding for the Compton scattering. Now, let's look at the key differences between Rayleigh and Compton scattering. So, we have the difference between their energy transfer. So, if you look at the table, so energy transfer, as for Rayleigh, there is no energy loss, which means it is an elastic scattering. And for Compton, we have the partial energy transfer, which is again an inelastic scattering. We also have the difference between the photon energy, the type of electron, the ionization, the dominance, the material dependence, the effect on imaging, and the biological impact between these two scatterings. So those are the key differences between Rayleigh and Compton scattering. Or to sum it all up, gakuha tag mga key differences lang between these two types of scattering. So these are the differences between these two types of scattering. Okay. Now, let's focus more on, or let's dive into penetration. Okay, ganina na-discuss na to si penetration, but gamay lang a discussion on penetration. Now, let's dig deeper onto penetration. So, penetration characteristics of different types of radiation. For example, si alpha, baka si beta, si neutron, or even gamma and X-rays depend on the radiation's properties. So, when you say properties, it depends on the mass, the charge, and the energy, and also the type of material it passes through. So, understanding the penetration in the range of this radiation is very essential for applications like radiation shielding, we have the medical treatments, and also the nuclear safety. Okay, so let's discuss each of, we have here the penetration by radiation type. So we have the composition, the charge, the mass, the penetration power, and the shielding material of each of these radiation types. Now, as you can see here, as for the alpha, let's start with the alpha particles. So, ang composition niya, it consists of 2 protons and 2 neutrons, which is a helium nga nucleus. So, making them a large, heavy, and also positively charged. So, as you can see, charge is positive 2. The mass is heavy. We have the penetration power is low. So, as for the shielding material, sa paper, we have the skin and also the air. So, since low man ang iyang penetration power, so, mas gamay-gamay na po itong kailangan ng shielding material for this radiation type. Now, as for the beta radiation, we have, it consists of high energy, high speed electrons, and or positrons. So, si electrons is we have the beta negative, and positrons is the beta positive. So, ang charge will be -1 or +1. Okay, again, we have electrons or positrons man. And as for the mass, it is beta particles are lighter and have a smaller charge compared to the alpha particle. So, the penetration power of beta is moderate. And ang iyang shielding materials will be plastic, glass, or aluminum, which is from 1 to 2, typically from 1 to 2 millimeter nga thick nga aluminum. And then, the third radiation type is the gamma or the X-rays. Si gamma radiation, so these are again electromagnetic radiation. which are composed of photons with no mass or charge. So, zero ang iyang charge. And, again, wala siya mass. Again, no mass or charge. So, zero ang mass and also the charge. But as for the penetration power of gamma particles or gamma radiation, high ang iyang penetration power. And the shielding material that we need for this one is, we have the lead. Kailangan na to lead, concrete, or steel, several centimeters thick. So, that is the penetration by radiation type. So, again, that is how we would determine the penetration of, depending on the radiation type. Okay. So, since na-discuss or na-mention naman gid nato si alpha, si beta, and si gamma, or even gamma rays and x-rays, so let's discuss more on each of these radiation types. So, let's start with the alpha particles. So, alpha particles, its interaction with matter, the range, and also the energy loss that is happening on these particles. So, si alpha particles, it consists of, again, 2 protons and 2 neutrons. So, si alpha particles are a type of ionizing radiation that interact with matter in unique ways due to their relatively large mass. We have a positive charge and high ionization capability. So, if the particles or these alpha particles pass through matter, pas ang pag-lose sa iyang energy, which that's why limited lang ilang range, but it makes them highly ionizing. So, let's understand more of these interactions that is very critical for assessing the safety, especially in environments where alpha emitting materials are present, as well as for the designing methods to measure and protect against the alpha radiation. Now, what is the range of alpha particles? Now, in air, the typical range of alpha particles in air is on the order of few centimeters, more likely 2 to 10 centimeters, depending on the initial energy of the particle. So, kani siya nga short range makes the alpha radiation undetectable over long distances. Okay, again, si alpha particles, paspas sila mag-lose of energy. That's why limited lang ang iyang range. Okay, so how about in solids or in liquids? So, in denser materials, the range is significantly shorter. So, for instance, the alpha particles can only penetrate a few tenths of micrometers into materials like, for example, the human tissue, the paper, or even plastic. So, even a thin layer of skin or dead cells on the surface of the body is enough to stop the alpha particles. Okay, again, low man ang iyang penetration power. So, ang iyang range is shorter yet. Okay. Now, how about the alpha particles' energy loss mechanisms? Now, as the alpha particles travel through matter, so they lose energy primarily through the interactions with the electrons in the atoms of the material, resulting to ionization and excitation. So, let's discuss the mechanisms of the energy loss of alpha particles. And let's start with ionization. So, sa ionization, now due to their double positive charge, the alpha particles strongly interact with electrons in the material, knocking them out of the atoms and creating ion pairs. So, this ionization process causes the alpha particle to lose energy rapidly. So, muna si ionization. The second one is the excitation. As for excitation, the alpha particles can also transfer energy to electrons without ionizing them. So, raising the electrons to higher energy levels. So, kani siya nga process consumes energy and contributes to the energy loss of the alpha particle. And then we have the stopping power. So by the way, what is a stopping power? So a stopping power of a material refers to the rate at which an alpha particle loses energy as it moves through the material. So for our alpha particles, ang stopping power niya is high. It's because, again, they have a large mass and charge. So ang stopping power is higher in denser materials, meaning the alpha particles lose energy more quickly and have a shorter range on these substances. And then, as for the last one, the mechanism is we have the Bragg peak. So now, as the alpha particles slow down, they deposit their energy more densely near the end of their path, forming a Bragg peak. So this means na most of the ionization and damage occurs just before the particle comes to a stop. So this kanang property is particularly important in medical applications like proton therapy, though the alpha particles are less commonly used for treatment. Again, it's because of very low penetration power ni alpha particles. Now, what are the implications for safety as for alpha particles? Now, as for the external exposure, since alpha particles cannot penetrate the outer layer of human skin, so the external exposure to alpha radiation is generally not a significant health hazard. So even direct contact with an alpha emitting source will not lead to skin damage unless the material is in close proximity to, let's say, open wounds bakaha or mucous membranes. So that is the external exposure. Now for the internal exposure, the primary risk from alpha particles comes from internal exposure. So dili siya sa external exposure but on the internal exposure. So if alpha emitting materials are inhaled, ingested, or enter the body through a wound, they can deposit a significant amount of energy in a small volume of tissue, leading to serious biological damage. So kung sa external exposure, wala lang siya dili significant ang iyang hazard, but when it is inhaled, ingested, or even it enters the body through wounds, makakause gid siya og serious biological damage. So the alpha particles are highly ionizing. It's because they are highly ionizing. They can cause DNA damage, increase the risk of mutations, and potentially lead to cancers, especially in the lungs, the bones, and also other organs. So that is the implications for alpha particles in an internal exposure. And then as for the shielding and containment, while alpha particles are easily shielded by simple materials, that is, for example, paper, skin, or plastic, the containment of alpha emitting materials is crucial daw to prevent internal exposure. Okay, again, mas serious ang damage sa internal kaysa sa external. So in industrial, medical, or research settings where alpha emitters are present, controlling the spread of radioactive particles, that is through ventilation or protective barriers, is vital. So it's very important to control the spread of the radioactive particles, which is again through ventilation or protective barriers. Now, how do we measure alpha radiation? So as for measuring alpha radiation, we have number one, the alpha particle detectors. So alpha radiation can be measured using several types of detectors, so each suited to specific environments and levels of radiation. So first one, we have the scintillation detectors. Second one, we have the solid state detectors, and we also have the proportional counters. So kani sila nga mga detectors muna sila ang makadetect sa alpha radiation or different types of detectors na makadetect of alpha particles. And then, second way of measuring alpha particle is through surface contamination monitoring. So, because alpha particles cannot penetrate most materials, so measurements of alpha radiation typically focus on surface contamination. So, the smear test, we call them a smear test, are often used to detect the presence of alpha emitting materials on surfaces where a wipe daw is used to collect particles for later analysis. And then, the third measurement of alpha radiation is the air sampling for alpha emitters. So, in environments where alpha emitting gases such as radon, so by the way, si radon is an alpha emitting gas. So, in environments where alpha emitting gases are present, air sampling and subsequent measurements are used to assess the level of alpha radiation. So, the filters are used to capture alpha emitting particles which are then analyzed in controlled setting. So, those are the measurements or how we would measure the alpha radiation. So, that's it for alpha radiation. Now, let's proceed to beta particles. So, beta particles, its behavior in matter, the range, and also the energy transfer. Now, what is the range of beta particles? So, beta particles have a moderate range compared to alpha particles. So, meaning their range is greater in air and less in denser materials like water or tissue. So, again, in air, the beta particles can travel several meters depending on their energy. So, for example, a beta particle with an energy of around 1 mega electron volts can travel about 3 to 5 meters in air. So, inana kalaya ang matravel ni beta particles if ang iyang energy is around 1 mega electron volt. Now, how about in solids or liquids? Now, as for solids or liquids, sa tissue, beta particles with energies in the range of 100 kilo electron volt to 1 mega electron volt typically have a range of few millimeters to about 1 centimeter in the human tissue. So, kani nga tissue nga mean is the human tissue. So, this range means that they can deposit their energy in skin or near surface tissues, posing a significant hazard if they enter the body. And as for the shielding materials, beta particles can be effectively stopped by materials such as plastic, glass, or even aluminum. So typically, a few millimeters of plastic or aluminum is sufficient or are sufficient to block beta radiation. Now, how about the energy transfer and also its interaction with matter? So, beta particles, they lose energy as they interact with the electrons of the atoms in the material nga they pass through. So, kaning interactions will lead to ionization, excitation, and in some cases, we have the Bremsstrahlung, production of Bremsstrahlung radiation. So, we will be delving into each of this one. So, let's start with ionization. So, the primary mechanism for energy loss by beta particles is ionization. So, as particles or as beta particles pass through matter, they collide with atomic electrons, transferring energy and ionizing the atoms. So, the amount of energy lost per unit distance traveled is proportional to the particle's velocity and the density of the material. So, that is ionization. As for excitation, now in addition to ionizing atoms, beta particles can transfer energy to electrons in atoms without fully ejecting them, which again causes excitation. So, kaning mga excited nga atoms may later release this energy as light or heat. So that is excitation. And then the third one is the bremsstrahlung radiation. So now, as beta particles decelerate when they pass through materials, when they pass through materials, makuhaan ang ilang energy, or there is an energy loss that is happening. So, particularly in dense or high atomic number materials like lead, so they may lose energy through the emission of bremsstrahlung radiation. So, kani siya nga phenomenon occurs because the beta particles' high-speed motion near a nucleus causes a change in direction and an emission of X-rays. So the bremsstrahlung radiation becomes more significant with higher energy beta particles and materials with higher atomic numbers, or Z, leading to additional radiation that needs to be considered in shielding design. So, meaning to minimize bremsstrahlung production, so low atomic number materials like plastic baka or acrylic are often used as beta particle shields instead of higher atomic number materials like lead. Now, how about the stopping power? Again, the stopping power describes the rate at which a beta particle loses energy as it passes through the material. So, this is highly dependent of the energy of the beta particle and also the density of the material. So, meaning denser materials have higher stopping power and reduce the range of beta particles more effectively. So, that is the stopping power of beta particles. So, ang denser materials daw have a higher stopping power, and also it reduces the range of beta particles more effectively. Now, with regards to the interactions with different materials, we have number one. The first one is the low atomic number materials, which is the plastic, for example, plastic, water, or tissue. So, as the range and energy loss, so in materials with low atomic numbers, beta particles lose energy primarily, again, through ionization and excitation. So they can travel several millimeters or even centimeters before losing their energy. And as for shielding, materials like plastic, acrylic, and also water are effective for shielding beta radiation because they minimize the production of bremsstrahlung radiation while still absorbing the beta particles. So, thin layers of plastic or glass are often sufficient to stop the beta particles. And as for the medical and biological impact, so like biological materials like tissue, si beta materials can penetrate a few millimeters to centimeters, again depending on the energy of these beta particles. So the beta radiation can damage the skin and superficial tissues, potentially causing burns or radiation-induced lesions. So internal exposure to beta emitters, let's say from ingestion or inhalation, can cause significant tissue damage as beta particles deposit their energy within the body. And as for the high atomic, katong gaganina is the low atomic number materials. What about the high atomic number materials? For example, we have the lead and the steel. So we have the bremsstrahlung radiation. So the beta particles, so in these materials, high atomic number materials, the beta particles can generate bremsstrahlung X-rays. So increasing the overall radiation exposure. So kani siya nga process becomes more significant with increasing beta particle energy. And as for shielding considerations, So, while the high atomic number materials can stop beta particles, the Bremsstrahlung radiation nga gina-generate sa beta particles must also be shielded. So, para ma-address ni siya, kani silang mga low atomic number materials are often placed in front of the high atomic number materials to absorb the beta particles, while the high atomic number material absorbs the Bremsstrahlung radiation. And then, as for the range of this high atomic number materials, ang range ni beta particles is shorter daw than in low atomic number materials due to greater density and atomic structure, which enhances energy loss through collisions with the electrons. Now, how about for the range and energy dependence of the beta particles? So, sa low energy beta particles, which are below 100 kiloelectron volt, so they can be easily absorbed by thin materials like paper, skin, or a few millimeters of plastic. So, ang ilang range is limited and they are less penetrating than high energy beta particles. So, kani si low energy beta particles. Whereas si high energy beta particles, ang iyang range is in the mega electron volts na, can travel several meters in air daw, and few millimeters to centimeters in solid or liquid materials. So they require thicker shielding to absorb and stop them, and they can generate again the Bremsstrahlung radiation if the high atomic number materials are used for shielding. Now, as for the safety and measurement, we have the safety considerations. So, we have the external exposure, the internal exposure, and the Bremsstrahlung shielding. So, si beta radiation, sa external exposure, si beta radiation can cause burns and tissue damage, especially if the source is in close contact with the skin. So, kung si alpha, ang yang external exposure is wala lang, si beta radiation can cause burns and tissue damage. So, as for the internal exposure, if ma-inhale siya, ma-ingest, or musulod siya sa atong body through wounds, they can cause significant damage to tissues or organs. For example, kaning mga beta emitters like strontium-90 or iodine-131 can be very dangerous if they accumulate in specific organs. Let's say, for example, sa atong bones baka or sa thyroid. And also, it emits radiation from within the body. And then, as for the Bremsstrahlung shielding, so a shielding must be carefully designed to account for the Bremsstrahlung X-ray. So, again, we need the combination of low atomic number materials para stop ang beta particles, and we also need the high atomic number materials to absorb the Bremsstrahlung radiation. Now, how about for the measurement of beta radiation? Kaya naman ta sa safety considerations. How about for the measurement of beta radiation? So, we have the first one, we have the Geiger-Müller counters or GM counters. So, we also have the scintillation counters. And we have the proportional counters. So, muna sila ang mga counters that can measure the amount of beta radiation that is entering on a system or a body. Okay, so we are done with alpha and beta particles. Now let's proceed to the third one, which is the gamma rays and X-rays, including their interaction with matter, attenuation, and also absorption characteristics. Now, as for the attenuation and absorption of gamma rays and X-rays, so as they pass through matter, ang ilang intensity decreases due to the interactions with the atoms in the material. So, kani siya nga process is referred to as attenuation. So, the attenuation of gamma rays and X-rays involves both absorption, where photons are removed from the beam, and also scattering. So, again, they involved absorption and scattering during the attenuation of the gamma rays and X-rays. Now, we have here this formula. So, this is the formula to calculate the intensity of the radiation of gamma rays and X-rays. So, here we have, again, this is our formula, and this is what it means by the following variables. Now, the mechanisms of interaction, or the primary mechanisms by which gamma rays and X-rays interact with matter, are the photoelectric effect, the Compton scattering, and the pair production. Now, let's discuss all about the attenuation coefficients. Kaya na-discuss man nato ang mechanisms of interaction. Now, let's have the attenuation coefficients and also the material dependence. So, we have two. We have the linear attenuation coefficient and we have the mass attenuation coefficient. So, si linear attenuation coefficient, we have, it is described as micro variable, and then the mass attenuation coefficient is micro over, we have this, I forgot the name of this one, rho. Okay, so kani sila, si linear attenuation coefficient, this describes how much the intensity of gamma rays or X-rays decreases per unit thickness of the material. So it also depends on the material's density and the photon energy. Whereas the mass attenuation coefficient is normalized by the material's density. So it allows for comparison between different materials regardless of their density. Now, what about the shielding considerations for gamma rays and X-rays? So shielding gamma rays and X-rays requires careful consideration of the photon energy. We have the material's atomic number and the potential for secondary radiation like Bremsstrahlung. So for low energy X-rays, thin sheets of lead or similar high atomic number materials are effective at shielding low energy X-rays, which are used in medical imaging, for example. Whereas for the high energy gamma rays, we need thick layers of lead or concrete to shield the high energy gamma rays. So however, in high energy applications, now care must be taken to account for Bremsstrahlung radiation produced when gamma rays interact with the shield. So those are the shielding considerations, again, with the low energy X-rays and the high energy gamma rays. Okay, so we are done discussing with the different radiation types. We have again the alpha, the beta, the gamma and X-rays, gamma rays and X-rays. Now let's talk about linear energy transfer, or also known as LET. Okay, so LET, or the linear energy transfer, is defined as the amount of energy deposited by a charged particle as it travels through a material per unit length of its trajectory. So mathematically, it is expressed as, so this is the formula for linear energy transfer, dE over dx, where dE is the energy lost by the particle and dx is the distance traveled through the material. So typically, LET is measured in kilo electron volt over micrometer, or kiloelectron volts per micrometer. So it represents the energy loss over a small distance in the material. Now, what are the types? How about the types of radiation and the linear energy transfer? So, ang different types of radiation mango, they exhibit different let values. So, depending on their mass, their charge, and also their velocity. Now, as for the low let radiation, it includes, ang low linear energy transferring radiation includes X-rays, gamma rays, and beta particles. Whereas for the high let radiation, it includes the alpha particles, protons, and heavy ions. So, muna ang sa low let radiation manggod, they transfer relatively small amounts of energy over a large distance. That's why it results in a low let radiation. Whereas sa high let radiation, these particles transfer large amounts of energy over a shorter distance. So, resulting in a high linear energy transfer. The factors that is affecting or that are affecting the linear energy transfer. So, there are several factors that influence the linear energy transfer of a radiation particle. So, we have first one is the particle mass, which means that heavier particles have higher let because they interact more strongly with the electrons in the material. So again, ang first factor is the particle mass. The second factor is the particle charge. So high charge particles, for example, the alpha particles, they transfer more energy to the material, which increasing the linear energy transfer. And then we have the particle energy and also the material type. So those are the four factors that affects the linear energy transfer of a radiation particle. Now, let's look at the let values for different types of radiation. So, muna siya, as for the alpha particles, we have 52-200 kiloelectron volts per micrometer. For protons, we have 0.5 to 20. For the beta particles, we have 0.2 to 0.5. For the gamma rays and X-rays, we have 0.1 to 0.3. And for the neutrons, we have 5 to 50. So, muna siya ang mga values sa linear energy transfer depending on the radiation type or different types of radiation. Now, here are the implications for the radiation effects. We have the high let radiation, which are the alpha particles and the heavy ions. So, it causes localized severe damage at the cellular level. It is particularly harmful when internalized or it is taken through inhalation or ingestion. And also, high let radiation has a high relative biological effectiveness or RBE. So, meaning it causes more biological damage per unit dose compared to the low let radiation. And also, it is used in applications where targeted damage is needed. For example, the alpha particle therapy for cancer. So, that is the implications for the high let radiation. Now, for the low let radiation, we have again the beta particles, the gamma rays, the X-rays. So, it causes diffuse damage over a wider area, leading to less severe siya, but more widespread biological effects. So, it has also lower RBE or again relative biological effectiveness compared to the high let radiation, but it can still be harmful, especially at high doses or long exposure types. And also, low let radiation is used in diagnostic imaging, which are the X-rays, and also external therapy for the gamma rays. Okay, for the implications for radiation protection. Now, as for high let radiation, the external exposure daw is less concerning due to limited penetration, but the internal exposure requires stringent protection measures such as preventing inhalation of alpha emitters. So it requires containment and controlled handling to avoid ingestion or inhalation. Okay, again, si alpha particles manggod are very dangerous when it is inhaled or ingested. So, grabe ang yung internal exposure compared to external exposure. Now, for low-let radiation, the external exposure is a major concern due to deep penetration. So, shielding materials or shielding strategies must focus on the dense materials such as lead to absorb and attenuate gamma rays. And also, PPE or personal protective equipment and environmental shielding are critical in environments where gamma or X-rays are present. Okay. This will be our last topic that we will be discussing, which is all about radiation dosimetry. Now, if we will define radiation dosimetry, it is the science of measuring and assessing the amount of energy deposited by ionizing radiation in matter, particularly in biological tissues. So, ang key concepts nato for the radiation dosimetry, it includes the dose rate, and also the absorbed dose. Also, we will be discussing all about the absorbed dose, the equivalent dose, the effective dose, and the dose rate, and also with their together with their formulas. Okay, let's start with the absorbed dose. So, si absorbed dose daw, by definition, is the amount of energy deposited by ionizing radiation per unit mass of material. So, it provides a measure of how much radiation energy has been absorbed by the material. So, ang unit for the absorbed dose is gray or GY. So, it means that si 1 gray is equivalent to 1 joule of energy per kilogram of the material. So, here is the formula of the absorbed dose. D is equal to E over M. So, D is the absorbed dose, E is the energy deposited, and M is the mass of the material. So, that is the absorbed dose. Now, how about for the equivalent dose? So, the equivalent dose accounts for the type of radiation and its relative biological effectiveness or RBE. So, ang unit ni equivalent dose, kung si absorbed dose is in terms of gray, si equivalent dose is in terms of sievert or sieverts, SV. So, this is the formula of the equivalent dose. We have H is equal to D times WR. So, H is the equivalent dose, D is the absorbed dose, and WR is the radiation weighing factor. And then, as for the effective dose, so the effective dose daw is a more comprehensive measure that considers the sensitivity of different tissues to radiation. So, ang unit also of the effective dose are in terms of sievert or sieverts, if plural. And this is the formula to solve for the effective dose. So, if E is equal to the sum of WT, so WT is the tissue weighing factor, and HT is the equivalent dose in a specific tissue or organ. So, we also have the dose rate. So, the dose rate is the rate at which radiation dose is delivered or absorbed over time. So, ang unit ni dose rate is grays per second or sieverts per hour. So, muna siya ang unit for the dose rate. And for the formula, we have D, na dot here, is equal to D over T. So, D dot is the dose rate in grays per second or sieverts per hour. D is the total dose, and T is the time over which the dose is delivered. So, what is the measurement of radiation dose and also the units nga ginagamit? So, let's understand the units. we have the gray. So again, ato na ning na-discuss si gray. The application of the gray is it used to quantify the energy absorbed by materials, including biological tissues, which helps assess the potential for damage. And for the sievert, so again, this is the definition of sievert and ang iyang equivalent unit. And the application for sievert is it used to quantify the potential biological effects of radiation, integrating both the energy absorbed and the type of radiation. So in measuring the radiation dose, we have the absorbed dose measurement. So these are the instruments and the procedure. We also have the equivalent dose measurement. Again, these are the instruments that will be used in measuring this radiation dose and the procedure. And we have the effective dose measurement. So again, the instruments and the procedure for this type of measurement. Now, as for the applications in radiation safety and protection, we have the first one is the personal dosimetry. So, ang purpose the personal dosimetry is to monitor radiation exposure of individuals, especially workers in radiation-prone environments, nga naa sa medical imaging and also nuclear power plants. So, here are the devices used. So, we have personal dosimeters such as badges or wrist monitors. And the application is it helps manage and record individual radiation exposure, ensuring compliance with safety standards and regulations. And then the second one is we have the radiation protection. So, ang purpose ni radiation protection is to implement strategies to protect people from excessive radiation exposure. And again, here are the principles. We have the time, the distance, and the shielding. And ang application ni radiation protection is to determine the necessary shielding and safety measures based on those measurements and predicted exposure scenarios. And then, we have the third one, which is the medical radiation. So, ang medical radiation, ang purpose niya is to ensure safe and effective use of radiation in medical diagnostics and therapy. So, as for the measurement, so monitor doses administered during procedures such as in x-rays and CT scans and also in therapies, which is in radiation therapy. And the application is to optimize dose levels to balance diagnostic benefits with minimizing potential harm to the patients. And for the environmental and occupational safety, the purpose of this one is to assess, manage radiation levels in the environment and workplaces. And as for the measurement, we have the regular monitoring of radiation levels and doses received by workers and the public. And the application is implement safety protocols and preventive measures based on assessments to protect the workers and the environment. So, in interpreting the dose measurements, we have the following. We have the health risks. So, for the absorbed dose, we have the equivalent dose and the effective dose. So, that is how we would interpret the dose measurements based on the health risks. And for safety standards, we have the regulations and the monitoring for on the dose measurements. So again, in interpreting the dose measurements, we have the health risks and also the safety standards. Okay, so that's it. So I hope you've enjoyed listening to our lecture video discussion, and we'll see you on our next one. Bye!